Okay, so I thought I'd do a little fun video here. Just kind of show I'm not just about LCDs. I took over the repair of these power supplies from Bob Tiffany, who did them for years, and he kind of retired out of the repair business. And I learned to fix these supplies, and as far as I know, nobody else is fixing them. So anyway, these are very, very difficult to fix. Okay, so here's what an FP29 looks like. Basically what this is a switching power supply, which by their design nature is a closed loop oscillator that does the AC transformers, makes the transformers smaller at a high frequency. And this thing's capable of 29 volts at about 15 amps. So it puts out quite a bit of power. And I just pulled it out of the box. Kind of rotate it around so you can see the front of it. Ain't much to it. On-off switch with a red LED. And the very first thing I'm going to do is not test it. And the reason why I'm not going to test it is, and this is, before I go too far on this particular video, I don't want people to use this as a DIY, because these things are not to be fooled with. One of the things that Bob Tiffany told me when I first started working on these is the very first thing you need to do, Andy, is you need to buy an isolation transformer, which I purchased. And the reason for that is things that look like grounds in here aren't grounds. And this thing will hold, and the reason why I'm not going to plug it into the AC power and try to turn it on is even if it doesn't come on, the capacitors in here will be charged to 350 volts. And I've seen them still have voltage in them 15 minutes after I've disconnected them. So I'm going to go right ahead and take this thing apart and see what it looks like inside, see if there's any obvious issues. And then we'll proceed to work through the testing portion. So stay with us. One of the things I do, which I've shown on some of my radio repair videos, is I take the screws out and I will actually tape them with masking tape to the side of the chassis. And what this does is it does a couple things. It makes sure I don't lose the screws because they're captive under the tape. And it shows me this, it has me available for each of the screw sets. For instance, this side, which has 6 screws in it, the other side has 4. Those 6 screws are going to be taped right here to this side of the power supply. And when I'm putting this thing back together after it's fixed, I'll have my screws sitting right there. So that's what I do. Okay, so this is what an FP29 looks like inside. And here's the front end portion that makes the, there's a full wave rectifier, which is located underneath that insulation pad. There's also basically a dimmer switch right here that allows this switching power supply to do a soft start. In other words, everything has to come up to speed running before it tries to do output. So anyway, once this thing is fully up and running, it switches in this, I'm trying to think of the technical term, basically dimmer switch. It switches this in that right here are 2 series resistors, and sometimes these blow. These are thermal resistors. Basically what happens is if they overheat, they blow, and they've got they've got 5.6 ohms of resistance in each one of these. So there's 10 ohms of resistance in series. That current limits the inrush to this portion of the power supply. And then basically what it boils down to is these create the oscillation, the AC. This is converted from AC from the wall to DC, and DC here. This charges up the power supply. This puts a square wave on that high voltage, low current, relatively low current power, and then it allows you to use that transformer right there, and then it gets rectified back out with these diodes right here, back to DC, and then that's where you get 29 volts, and this also supplies 13 volts, and that's a separate little section right down here. 13 volts drives the radio, and this mainly, all of this 28 volts here is only used for the finals. So kind of interesting that the finals have power sitting on them even if the radio isn't turned on. So kind of weird, but that's the way the design works, and it does in fact work. These are for the Mark V's, and those are probably one of the most desirable Yaesu radios from the past, and people have them and love them. So anyway, we're digging in. Okay, so this is the assembly out of the chassis. We're going to dismount this. At the same time, we need to get rid of the clamps for the diodes, the rectifier, and the dimmer switch. So anyway, onward and upward. In the next segment, you'll see me with the board out, and we'll be doing some visual on the back side of this thing, see if we see any burnt traces or any of that kind of stuff. So hang in there. Okay, so we got the board out. Some people have asked me, why don't you actually show you taking things apart? And the answer is because I need two hands to do it. I'm a radio repair shop, not a video studio. So I can't take things apart. And if you've seen in some of my YouTubes where I've tried to do two things at once while holding the camera in my right hand and take stuff apart with my left, doesn't look too good. So anyway, so we're going to look at the back side of this board and see if we see any burnt traces. We do not. These things are getting old enough that there's actually, some of these I fixed with just nothing more than fractured solder joints, but those are very hard to find. There's also a weird thing that happens on these, and that is that the dimmer switch circuit, which is right here, and the circuits that go to that, these traces, oddly enough, the transformer itself vibrates at a very high rate, and quite often these lands right here, and I actually see a little bit of missing solder. Let's see. The solder mask itself, these literally fracture here from a continuous vibration, mechanical vibration that occurs with this transformer basically buzzing. And what that'll do is that it cuts out, it doesn't allow the dimmer circuit to cut in, and it actually winds up blowing those resistors that I showed before. So I'm going to get the microscope out and take a look at those and see if that's a problem, and I'll check and see if the resistors have the proper resistance, see if they're open. So one step at a time. Okay, the resistors are not blown, and it appears as though, I think there's a way to zoom in here. I think you can see a little bit of what I'm talking about there, but it has gotten to the point where it's actually fractured the trace. But you can see that there's some solder mask missing right off of that trace. Kind of a weird, interesting thing that happens. These things, I really find them fascinating to work on. The technology is really cool on switchers, and of course, honestly, if you know, the way things are going, everything's going to a switcher because nobody wants to lug around 30 pounds of copper and steel for big transformers. So everything's switchers. All these mean wells and so forth that you can buy at a really good price nowadays are all switchers. And I mentioned earlier that I wouldn't fire this thing up just to see if it worked, because if I had, I wouldn't be doing any of this right now, because these big caps, like I said, they hold about, they're in series. They hold about 350 volts in this area. And you got to wait about 15 minutes before you touch them. And there's no point in doing that. I'm certain that the customer is correct. It doesn't work. Okay, so before I dig in, I've got sort of a diary of notes here that I actually inherited from Bob, and I've made more notes to it. He was, sorry about that, he was a little neater than I was, or I am. I put red marking on this, but it basically gives me a cheat sheet on what voltages ought to be where. And I got a little trick that I can test most of the circuitry on this power supply at low voltage, which makes it very convenient and also very safe. The worst ones of these I've ever worked on are ones that people have just started shotgunning parts into them. And usually that doubles the cost of repair because it's a mess. It's a big mess. And so I prefer to get the virgin power supply just broken so that the failure modes and so forth make sense. One of the things that fails pretty often over time, that right there, believe it or not, is an IC chip, molded IC chip, and it is the brain and heart of the power supply. This is what sets up the oscillation. It gets feedback from the output to tell the power supply whether or not it needs more current. Again, for those who are kind of into the science, the output is coupled, the low voltage output is coupled to the high voltage input through a pair of opto-isolators, opto-couplers. And this is what drives the control circuitry. Sorry about the wires. The control circuitry is at this end. This monitors the output, does conditioning, lots of capacitance for the output to make sure that it doesn't have a lot of ripple in it. And also, as I mentioned, there's the 13 volt voltage source. So anyway, but very first thing we're going to do is confirm whether or not this guy is good. So we'll be jumping into that first. If that's good and the front end isn't shorted out, which it doesn't appear to be, because usually when something happens to the front end, there's the telltale sign of burnt PC boards and stinky smoke and all kinds of stuff. So it doesn't appear to be the case here. So my bet is either that guy's bad or the control circuitry section here has some of the Zehners have worn out and started getting leaky, and it's not getting correct feedback to the brain to make the oscillator portion of the power supply work. So really cool stuff. Just if somebody looks at this and wants to do this themselves, I am not responsible for anything. See this? That ain't ground. So in most power supplies, that's ground. So, and when I use the term ground, I mean earth ground. So anyway, onward and upward. Okay, so how many of these do I do? Enough to justify an inventory of just about every part in here, which this is how I store things. This is my FP29 parts bucket. I've got pretty much every kind of part in here that you possibly need to fix one of these puppies. And I do probably, I don't know, between 5 and 10 of these a year. Still, there's still plenty of Mark V's out there, and they're also used for other things because of the fact they're such a great power supply. So anyway, here we go. Okay, so I took the IC out, tested it, and actually reinstalled it even though it's bad, just to demonstrate the fix. So here we go. This IC is back in there, and let me lay this on my anti-static pad here. The new IC is right here, and we're going to show you that we already figured out what's wrong with this power supply. Kind of interesting. There's a little story or little, I don't know, blog, whatever the heck you want to call it, on the internet. And it's about this giant ship that's stuck in harbor for like 2 weeks, and all kinds of mechanics been working on it and tearing their hair out, and they can't get it. And here's $1 million ship stuck, and they call some super master guy that's supposed to be able to fix them. He comes out, opens his bag, takes a hammer, smacks the engine block. Engine immediately comes to life, works perfect. And he hands the skipper a bill for $10,000. And the skipper says, $10,000, you're only here a minute. And he said, okay. The invoice is broken down as follows. Hitting the engine block with a hammer is $1. Knowing where to hit it was $9,999. So anyway, I've literally seen and heard people working on these things for a week. And this is just tricks of the trade that you learn. So I've got this power supply here in setup right now to operate off of 13 volts with a 17 volt trigger mechanism. And that's how I test it. So in just a second, I'll show you what I'm talking about. Okay, so in my power rack here, I've got a 13 volt lambda supply, which is turned on. And this is going to be my turn on voltage that jumps over a bunch of circuitry. And when I apply 17 volts, that should pull current. And it's not. It's dead as a post. Nothing. Applying the voltage, nothing. So we're gonna fix the power supply now with a new IC. Okay, so the new IC is all installed. We're not gooped in yet because I always test and verify before I say it's done or fixed. There's the old IC. $100. Yaesu, I don't know if they still sell them. They were selling these things for $100. I don't pay $100 for these things. I found a direct source that I can get them significantly less than that. But anyway, they ain't cheap. But this thing's served well. It's probably been working for, I don't know, 10, 20 years. So its time has passed. So new one's in. And what we're going to do is we're going to test this real quick and see if I knew what part of the engine block to hit with a hammer. So here we go. We're going to go back over and look at the power supplies. Okay, so here's the power supplies. I want to put in 13 volts. Here's my control voltage. There we go. Saw the inrush current. And now power supply is running. You want to see something cool? Watch this. I just turned off the control voltage, and the power supply is running all by itself. So now this power supply is running off of 13 volts. Anybody want to guess what the output voltage is? Think about it for a minute, and then continue to watch the video. If you think a switching power supply ain't cool, this thing is putting out 29 volts, which is what it's supposed to be putting out. So I've got this power supply running off of 13 volts as opposed to 120 outlet. And it's actually running off 13 volts DC. And it's putting out the proper regulated voltage. Now, would this supply current? No. If I put any load on this thing, it would shut down. But I found it absolutely interesting when I first developed this approach, that this power supply will tell me if the control circuitry and everything's working with 13 volts. Okay, so long before I started fixing these, one of the things that Bob sent me was a fix. You saw me turn this power supply on with 17 volts. And apparently what happens in the design is if that voltage continues to climb, if the power supply doesn't turn on. So in other words, you plug the power supply in, you turn it on, and for some reason the power supply doesn't come up, doesn't start running, that voltage, that 17 volt circuit will continue to go up in voltage and actually blow out the IC, which is that strip of contacts right here. Those are the legs of the IC right there. Anyway, long story short, came up with a fix, and that fix is to put an 18-volt Zener in here so that it doesn't allow the voltage to climb past the required turn-on voltage, and that protects this IC. So every one of these that I work on, I do this fix to. Again, it was part of the inherited knowledge that came over from Bob, who I'm very grateful for. Anyway, the other thing I'm going to do is I mentioned earlier about the little failure point here for the oscillating, vibrating power supply transformer. So I am going to beef up, I'm going to scratch some of that solder mask off. I'm going to actually beef up that those two connections so that that won't fail. This power supply should be good for quite a while. Everything else, the control circuitry all seems to be working fine. So if it ain't broke, I'm not going to fix it. Because one of the things I've learned over the years is sometimes you can make some additional unbroke changes and find out that infant mortality sets in, or the part is just not as good or something. Now, all the parts I buy, I've obviously fixed a lot of these power supplies. Well, maybe not so obviously. I have fixed a lot of these power supplies. So anyway, again, I pretty much know from experience now what typically fails. And I guess if I were going to talk about this in a little more detail, about 10% of the time, the front end of these things get whacked, and I've seen them get high voltage, very high voltage from lightning, etc., through the front end power supply, and components literally vaporized. This is what happens in this area. The IC chip, probably maybe 20% of the time, and the other 70% of the time, if the math's right, is the control circuitry. So most of the failures are in the control circuitry. A few of the failures are in the IC going bad, and then mainly external damage. Now, I've also had them damaged the other way, and that is lightning coming in from the radio. That's the connector that goes to the radio, by the way. Lightning coming in from the radio and taking out some of the filtering and so forth. I've actually seen some of these capacitors that are only legs, that everything else is gone. So pretty much seen it all. But anyway, I'm going to tweak this thing up and give it some little fixes for longevity, and start packaging this thing back up. Okay, so overprotection voltage Zener is in. Tweaked up the lands on the solder, removed the solder mask and tweaked up the lands on this soft turn-on circuit connection, and gooped the IC in place. So ready to start bolting things back up. Again, kind of a little fun thing here. I mentioned how I tape things up. I'm about to anchor these diodes down, and right next to the screw holes are the parts. So ready to present themselves. So I go through a lot of masking tape, but I'll tell you what, it is worth it. Okay, so everything's back in. We're ready to go with the 120 volts. I've got this big old Variac up here. There's my spectrum analyzer. Love that old guy. Built like a tank. Okay, there's my Variac. And the reason why I'm going through a Variac is because the Variac is hooked to the isolation transformer, and I'd like to be around in case I put my finger where it doesn't belong. So this will certainly help me. Anyway, so what should happen now that I've got this plugged in is when I turn on the switch on the Variac, there should be a little electron, or basically it's an electrical tick, for lack of a better term. There's no relays or anything in this thing. It's actually sort of the electromechanical things happening. So when I turn this switch on, that Red light in a couple seconds should come on. Uh-oh. Nada. Well, that's not good. So, all right. What am I doing wrong? Step back and take a big look. Okay. That's all good. Ow. There it is. If you want it to work, you got to plug it in. So let me stick my fingers in there without the phone in my hand. We now have the incoming voltage plugged into the power supply. That's the, there's a external fuse that is on the back of the supply there. And then there's a fuse internally. So anyway, all right, I bet the light comes on now. Here we go. If you heard the tick, I can pick this up or not. Just listen. This is kind of, again, I think these supplies are so cool. Listen. Hear that tick? Gotta let it bleed down here. There we go. Lights off. Bled down. Listen. That's purely electromechanical magnetics kicking in. So I found that find that fascinating. So anyway, now power supply is making 30 volts, and that's because there is zero load and a ton of front end. So fan is running, which tells me that 13 volts is working, but we'll verify that anyway. So let me hook up, make sure the 13 volts is working. Again, wish I had more than two hands. There's the 13 volt portion. That's working too. Again, a little on the high side because there's no load. Okay, so how do I know this thing will in fact produce all of the current that it needs with the testing I've done so far? Answer is I don't. That's why we purchased another tool here, and I'm going to show you that in just a second. Okay, this is an electronic load. The power supply is turned on right now. The load is not, and you'll know the load because it's got a fan that will come on as soon as I start hitting this thing with some significant current. So the power supply is in fact running. You can see the fan is turning. I'll give this a bath when we're all finished here, by the way. Clear out all this dust, and we'll clean off the outside too. But anyway, by the way, this is to show you that this doesn't happen like once a year. That's one's waiting for a check to go out. So from the customer. It's all fixed, tested, and ready to go. So I'm going to turn on the load here. And what's going to happen is I'm going to start to turn this knob. And when I do, I'm actually stepping up the current, or actually the wattage, and you'll see the current begin to jump here. So there's 10 watts, 20, 30, 40, 50. You can see the current coming up. So let me just crank this puppy up. There's 280 watts, 9 amps. You can hear the load is getting warm. There's 13.8 amps, 400 watts. And I don't keep this here long because I want to keep this load alive. There we go. So this power supply just put out 13 amps at basically 29 volts. You can see the, let me turn this on again. I think it'll jump right up. Yep. You can see the voltage is at 28 volts, which is its spec, right about 29 volts. So that's under full load. I'll tell you a real quick story here. When I started working on these things, I was trying to figure out, okay, how can I test these things? And before I bought the nice economical load here, I tried different things. And one of the things I tried was, I think I read it somewhere, was landing lights for an airplane. Take 28 volts, takes 28 volts. So I put put one of those on one of these things, turned it on, and I was seeing spots for days. I mean, that's the brightest damn light I ever saw in my life. So I still got them. If anybody needs some landing lights for like a Piper Cub or something, let me know. We got a aircraft supply store about 3 or 4 miles from here. That's where I got them from. I have absolutely no use for them. And the other thing it did was, not only did it practically blind me, but it put out so much heat that, I mean, I've seen these ovens now that heat with light. It puts a microwave to shame.